So a stat teacher wants to see whether there's a difference in ages between day students and night students. Random sample of 35 students from each group. The data is given. Test to claim there's no difference in age between the two groups. Alpha is 0.05. So we're not talking about standard deviation. We're not talking about proportion, so it's got to be mean. And the two classes, day and evening, have nothing to do with each other. There's no correlation. There's no matching. There's no pair up. So it's independent. So we have two parameters. Mu D is the mean age of the day student, and mu N is the mean age of a night student. Our hypothesis, H naught, is mu D is equal to mu N, and the alternate is mu D is not equal to mu N, because we're just trying to see if there's a difference. Next, we look at our assumptions and conditions. It says that it is random, so it's an SRS, and both samples, 35, are greater than 30, so it's approximately normal. It is a two-sample independent t-test. T-test because we don't have sigma, and we're not going to have sigma, and it's two-tailed. So we need to find our data, our x bars, our s's. If we're using GeoGebra, you type in your data, one variable analysis, and you click on your show statistics. We get our mean and our standard deviation. We're using S, not sigma, because this is from a sample. Same thing with our second set. We get our mean and standard deviation. Now, we can type it into our calculator, and if we label it, the calculator will calculate it for us while we're doing the test. We'll Control I and go to a calculator page, and we're going to run our test. Statistics, set S, two sample t-test. We're using data. Labeled in V1 and E1, it is two-tailed. So it found our X bar for both of them and our S's. It didn't give us sigma, it gave us S's, and that's what we wanted anyways. It gave us our T value, our T score, and our P value. If we're using GeoGebra, we have to do t-test difference of means. Mu1 minus mu2 equals 0 is the same thing as mu1 equals mu2. We want two-tailed, and we have to type in our data. So here, it's going to be rounded because we rounded the mean and standard deviation. And when we run it, we get the same t-score and p-value. Now, if we want to do classical, we need to have our cutoff. Our alpha was 0.05, and it was two-tailed, so we have to divide it by 2. Degrees of freedom, we use 34. We use the smaller of the two. And we cut our alpha in half, so negative 2.03 over here, and because it's symmetrical, 2.03 over here. We're using the calculator. It would be under Menu, Statistics, Distributions, and Inverse T. Always area to the left, and degrees of freedom. So negative 2.03, we can do the same thing for the right side by putting in 0.975 and get positive 2.03. So this is what our distribution looks like. Our cutoffs are negative 2.03 and 2.03. Our t-score, negative 1.6798, is not in the critical region. It's in this unshaded region, so we fail to reject. When we do our p-value, it's 2 times, because it's a two-tailed test, the probability of t less than negative 1.6798. It's less than because it's negative, and we get 0.0976. That is obviously not less than 0.05, our alpha, so we fail to reject. If we're doing a confidence interval, and again, we don't have to do all the methods, but you can choose your method. We're doing a confidence interval. We go to Statistics, Confidence Intervals, and it's a two-sample t-interval. Use data. Again, we use D1 and E1 to label what we're dealing with. Our alpha is 0.05, so our confidence level is 0.95. It's the complement. Again, it found our X bar and our S for us if we needed it, and it gives us our lower and upper bound of our confidence interval. If we're using GeoGebra, we're going to our estimates. T-estimate difference of means are already in here from before. Check our confidence level is what we want, and we get the same lower and upper limit. I went a little crazy on my rounding, so I'm going to change that back a little bit. So that's all we need. So our confidence interval is negative 2.81 to 0.24. Now, we want to see if mu d equals mu n. Well, if that's true, then mu d minus mu n would be 0, and 0 is in this interval. It means this is a pretty good guess, and so we're pretty close to mu d equaling mu n, so we fail to reject. We're always looking to see if 0 is in there. So we have insufficient evidence to reject the null. Ergo, we cannot support the claim the mean age of day and night students are different based on our sample at alpha equals 0.05. So even though we had a low p-value, it wasn't low enough to say that they are different. So we're sticking with that they are same. The p-value, 9.76%, is the probability that the two sets are the same based on our mean, or the two means are the same based on the data that we have.